Right. So the yeah. If you click on the point, it will just show you. Yeah. So this is what you're seeing here is essentially you build your system. We saw how to build a system, right? Sys is equal to transfer function, and then you specify the numerator and the denominator. Cell phones, is it that important? This is something I would like you guys to think about, okay? So you have heard about these quadrants. There are everything you do in your life, if you think about them as important and urgent, okay, or not important and not urgent. You can classify every task in as one of these, either important, not important, urgent, or not urgent. Okay. There are tasks which are not important and urgent, not important and not urgent. Okay. Important and urgent, and important but not urgent. Okay. This, you should try to completely avoid doing these tasks. Not important, not urgent. These include something like that. You don't really need, it's not important, it's not urgent, checking your cell phones. Especially if you're not doing anything productive, you don't really need to do it. Even for that matter, watching TV, right? You don't really need to do this. Not important and urgent. So these are your day-to-day tasks. For example, brushing, right? Or taking a shower. Those may be not important, but you should do it. You cannot not do them, right? It's not, if you don't do it, it will not be like you're going to do. But there are some things which are urgent. You have to eat food, right? You have to do them, but they are not really important. So now, most tasks will start here, okay? We'll start at important and not urgent. If you ignore them, they tend to slowly go into important and urgent, slowly start becoming, right, homework. So homework is important, but it is not urgent when given in time. If you start in time. But if you wait, it will go into important and urgent. Right? And this is when you compromise your quality. When it becomes important and urgent, you may compromise on quality. This is it's let's say it's a leadership lesson. Okay, you can think about it in the context of, if you want to become leaders, you cannot do this. If you want to become leaders in careers, or if you want to build a successful career, you have to, I wouldn't say completely ignore it, but you have to give less and less importance to these, and potentially you should just get rid of them. Only then you can become a successful leader. And you should read Dr. Johnson's Washington Word on a daily basis. Yeah. I read it every day. It's there in your mailbox if you subscribe at 8 o'clock with your breakfast, or just read it. It gives you a perspective of how rich this university was once. Today it's not in that good state, but you can figure out and you can learn things like this. Okay, so Booker T. Washington never did these. If you look at, or never recruited anybody who did that. You can see, you can pretty much sense that. Okay, this is something to ponder about. All right. So we'll discuss a general second order system in the context of, or the performance characteristics in the context of an underdamped second order system. So here, how do you define underdamped second order system? Your poles are imaginary, right? Sorry, it's complex. Real and imaginary. You're right. So poles are complex. So if you look at the pole plot, you'll have something here. And we are always talking about second order systems, right? So it will have two poles, which are, and we are assuming everything is stable. So nothing on the right half plane, everything on the left half plane. So these, if you look at this, these are some of the transient characteristics of a second order system. So the first one you're going to see here is peak time. So what is the peak time? Time, say that again?
Whenever the system reaches peak.
Right. So this is what you're seeing here. Are you able to see this? You have this, you have Are you able to see the response of the system here? The blue color is the response. Okay? So this is a unit step response. That means the system is subjected to a unit step input. So peak time is the time taken for the system to reach its first peak, right? So this is that time. On the x-axis, you're going to see time in seconds, and on the y-axis, it says amplitude, but you can think about this as the response itself. Okay. So TP, the formula for TP is peak time. I'm not going to write the definitions. I'm sure you'll understand the definition, or if you need, you can actually just read it from the textbook. What is a peak time and all those. Okay. So this is the and you can derive these expressions, okay? This is the peak time, and what you're seeing here is the peak time, right? this visible or you want it bigger? I don't think we can make it bigger. Is this better? You can see the numbers better, right? Okay. So you can either do a LTI view and sys. Give sys in your MATLAB, yes? TP. This is pi. Okay. And then you have percentage overshoot. Okay. It's denoted by this and OS. Okay. So you have percentage overshoot is equal to e to the power of minus zeta pi 1 minus zeta square 200. So percentage overshoot is essentially this is the final response, right? Do you see the final response? The final response is this line, this one. Okay. It is essentially where the input is. Got it? The final response is this. When it starts tracking the input, wherever the input is, the response will eventually do that. Okay. So here, if I did, instead of LTI view, if we did, let's say, step, so this is exactly the same thing, just a so your 1 is the final response. Because it is unit step input and it will be a unit step response, your 1 is final response. So whatever the peak value above this 1, that would be your percentage overshoot. So percentage overshoot here would be, you see the response, what is the response here? The peak amplitude of the system? 1.25, right? So how would you calculate percentage overshoot? So you have 1.25 minus 1 over 1. So here the percentage overshoot would be 25.4%. Got it? Or if you're given just, step input is 1. It's unit step input, right? That unit means 1.
Yeah, so because it's 1.25.
1.25. It shoots by 25%. So it overshoots by 25%. So that is the percentage overshoot. So if you're given this form, you use this formula to calculate percentage overshoot. Okay? So if you're, so for example, here, what is the system? The system given is 25 over S square plus 4S plus 25, right? So from this, in your assignment and your exam, what you're going to do is, you're going to extract, what do you need for percentage overshoot?
You need the actual frequency and your damping.
Right. Here you just need the damping ratio for percentage overshoot. So if you just extract, the natural frequency is 5, so the damping ratio will be 4 over 10. Right? So you extract that, you substitute it over here, you're going to get this percentage overshoot value.
So we would give a graph. You just have to see what the amplitude.
Right. If you're doing a project, you can just point there and figure out what the percentage overshoot is. Yes. It's omega n. So if you want the peak time, again you extract omega n and zeta. And if you substitute, you'll get the peak time, the time taken to reach the peak. Okay. The next one is settling time. So settling time, it depends on how you define the settling time. Here, if you see, the settling time is defined as plus or minus 2%. Do you see it? So if I zoom in on this part, 2%, plus or minus 2%. Got it? So once the system reaches that 2% within that and stays within that. So when is the first time it reaches that 2%?
The very first time.
Right.
Right after.
It reaches here, right? The very first time. You see this? It reaches here. But it does not stay in that 2%. It reaches again here, but it does not stay. So here, after this point, it reaches that 2% and it stays in that 2%.
So to me, it seems like you would want a system with a fast rising time, a low peak time, and a quick settling time.
Right. Right. So that is something like that. You would have to design a critically damped system, which will give you all that characteristics in a single system. Okay. So critically damped system, the rise time and peak time will be a little more than this, but the settling time will be much sooner, much smaller. So it will just go, it may hardly peak or it may not peak and it will just do that. Okay, it will immediately stabilize. Settling time, the formula for settling time is Ts is equal to 4 over zeta omega n, and this is for plus or minus 2%. You can actually increase this. It depends on the system you're designing. In fact, I can show you here. So if you go to properties, you see that the settling time is defined as 2% here. You can actually change this to 5%. Now the settling time changes. Okay? Yeah. I think what I need to do is, I have this. I can change the limits, properties, options. So if I do 5, now if I do the peak time or steady state, see it is 5%. You see that? If I zoom in, I can show you that it is 5%. Plus or minus 5%. You see it? So you can change how you define the settling time. But again, rise time also can be, generally it is regarded as 0.1 to 0.9 of the final output. But you can change it from let's say 0 to 60, something like that. Characteristics, rise time, characteristics, peak response. Okay. Settling time,
if it was plus or minus 5%, how would that equation change?
this will probably be 10.
Okay,
yeah. You can actually derive your settling time to this value. See, everything is this, right? You have, if you look at this, and we are talking about step response characteristics, correct? So if you, what is the step response of this system or this system? Step response is C of S is equal to omega n square over S into S square plus 2 zeta omega n S plus omega n square, right? And your C of t would be Laplace inverse, correct, of C of S. Now you obviously you can find the roots of this equation, take the inverse Laplace, do a partial fraction expansion, take an inverse Laplace, and figure out what C of t is. Now if you want to apply something like this, what do you do? So your settling time is essentially we're defining it as plus or minus 2%, right? So you can say it is 1.2 times C of t, okay, right? So this is the 1.02, right? So it will be 1.02 and 0.98 C of t. So you apply some math to this and get to this settling time equation. Got it? It's if you want, you can derive the response yourself, or you can derive this equation yourself. It's available in the textbook as well, but it's not so relevant, or it's relevant, but you did not ponder much on this. If you just use this, you should be able to figure out how to do it.
Most cases it's 2%.
It's 2% or 5%. 2% is actually pretty strict, pretty stringent settling time requirements. Unless you're looking for very precise systems, you are talking about 5%, sometimes 10%. Right, 5%, yeah. So this will change a little bit in that case, okay. And for rise time, finally the rise time, there is no formula as such for rise time. We'll refer to figure 4.16. There is a formula, but let's not go there. And it's important that you understand how to use this this figure, or this. There's a table in this figure. Let me see if it's on a plot like this, it's very simple, right? You just have to do the characteristics. So here you see, what is this? Right, 0.293, but this is 0.9 times the. So this is that rise time. This minus this. Okay, so this point is, I think, 0.1. If I zoom in, characteristics and rise time. So rise time, it starts about 0.1. You see the 0.1 here? Almost. 0.1 to 0.9. The time taken for the system to rise from 0.1 of the final response to 0.9 of the final response. Antoine, I just told you this thing. Okay? So this is, you can do this. This table is very important. Especially for your lab, you'll use this. For your exam, what you're going to do is you don't have to memorize the formulas. You'll be given, you can make your formula sheet or cheat sheet and use the formulas. Okay? Hmm? 1 page is fine.
We're not going to need MATLAB for the next test.
How are you going to submit MATLAB though?
I was just asking because you said you offered it would be used in lab test stuff. I was asking.
I can do this. I can give you. We can have 2 parts. One would be just theory, and one would just be MATLAB. You can come here, and we can do it in the lab session. You sit here and do. It will count as extra credit towards the exam. You want to do it? You finally got his extra credit. Huh? So you want to do that? You're going to sit here and do MATLAB, just MATLAB. Hmm? Yeah. Hmm? All right. So I'll design 2 or 3 problems where, and you need to do your assignment and mail your solutions right away before you get out of the class. Yeah. Okay. And what I'll do is you might get slightly more complex problems if you were going to do MATLAB for MATLAB exercise, because you don't have to. Hmm? All right, let's do an example and wrap this up. So you have I will send out an assignment for this chapter next week, let's say Monday. Okay, but you have to understand that you'll use these formulas. You'll be given such a system and asked to figure out these, or what you'll be given is let's say this value and this value and figure out what the system is. Can you do that? Many of you are not able to do that. That has been my experience. So you have to think about settling time. Right. You should be able to do it because it is 2 unknowns and 2 equations. Right? You should be able to figure out what is the value of sigma or zeta and what is the value of omega n. And then once you found that, you substitute in G of S to give me the system. Okay. So given example, the pole plot, pole 0 plot, So let's say you're given this something like this. There is your omega n. So how is zeta d or sigma d or omega d expressed? Omega d is the damped frequency. Omega n is the natural frequency. Omega d is simply omega n into root of sigma one minus sigma square, one minus zeta square. Okay, this is how omega d is defined, and sigma d, or sigma d is defined as zeta omega n. Okay, this is the damped frequency, and this is the damping ratio. So you can just call it sigma d. Okay, so if you have this, what is omega d here? So you can say sigma d is equal to minus 3, right, which is zeta omega n, and omega d is equal to omega n into root of 1 minus zeta square, which is minus 3.
When you asked, when you said given rise time, peak time, would you be given a whole plot too?
No.
Okay.
So here it's slightly different. So here you are given this. You're not given the system itself. You're given the pole plot. And no, you're trying to find the system characteristics. So you can obviously find the system as well, but the question here would be to find zeta omega n Ts TP and percentage. Ts TP and percentage overshoot. Okay. So from these two you can find an expression for omega n and zeta, right? How do you find an expression for omega n and zeta? So you can either do that, or what you can do is, see, this is, let's say this is theta. Okay, your cosine theta is, tangent theta is what? See, this is theta. So tangent theta is omega j omega n over omega d. Okay. So zeta is defined as actually cosine theta, and theta here is cosine tangent inverse of 7 over 3. Okay. This is how zeta is. Zeta can also be defined like this. It's just defined as cosine theta. Okay. Right, exactly. So you could have simply used these two to figure out what omega n and zeta are, right? And then figured out the system, and then done your all these, or figured out the system, did a step response.
So we'll make it deep right there. have omega EP equal to -7.
Omega, yeah, you're right.
Because that's what I was just
Right.
now okay.
So this is 7, this is 3. So it cannot really be negative.
Yeah, it can't
So here this would come out to be 0.394. Okay. And omega n is simply root of 7 square plus 3 square. So this distance actually is omega n, and this angle is sigma. Okay. So once you do this, everything else is pretty simple. Your TP would be pi over 7.616 into root of 1 minus square. This would be this would be equal to 26%. If you substitute sigma value, you're going to get that. This would be 4 over 7.616.394, which is 0.33 seconds. Okay. It's very straightforward actually. Just try to understand the pole plot. System can be represented in different form. You should be able to understand the representation. That's it. And I'll give you example problems or exercises through which you'll ensure that you have practice for the exam.
So the exam is going to be on the homework just due Monday and then this homework.
Right. So there will be another homework on Monday. So exam will be on third homework and fourth.